So hello, good morning, everyone. Today we present week 2 lab for MATH102 with Jupyter Notebook. Let me share with you our screen for today's presentation and our Jupyter Notebook browser. So this is the presentation you should have with your recitation and structure this week. This is the outline of the presentation. We will solve the exercise we've seen at the end of week 2, and we will talk about areas and distances, which correspond to sections 5.2 and 5.3 in your current syllabus for 102. We'll finish with a couple of exercises. So let me start by exercise at the end of week 1. If we remember, we had this question where we were asked to write using Python a function that prints out f of x equals 3x minus 5. And we were asked also to find the value of f at x equals 1.3 and give it a parameter called q, then print q. We were also asked to plot the function and to find the x-intercept. So you should have on your blackboard the week 2 solution and week 1 exercise, this file with extension IP, Y, and B, which would be uploaded by your instructor. So this is the week 2 file for this week. And we will first start by re-importing the SymPy and the NumPy packages to start working on this problem. So in question 1, let's define the variable x and the function f of x, and then display. So as you've seen previously, we assume here, of course, that we already imported SymPy and NumPy as we did in week 1. So we will define x as a variable using SMP symbol and f as a function of x. And then we'll say that f is 3x minus 5, and we will display f using the display command or using the print command. Okay, so what you should do here, what should appear is 3x minus 5 when the display command is used, or f of x equals 3 star x minus 5 when the print command is used. Okay, so if I switch to the Jupyter notebook, I have my file here, which is ready for my recitation. This is the solution I used for question 1. And this is what I get when I do shift and enter or when I run my code. So this is, I put all the questions in one. So this is the first display here, 3x minus 5, what you see here, 3x minus 5. Okay, I'll go back to my presentation. So question 2, we would like to find the value of f of x at x equals 1.3. For this, we use the function subs. What does it do? It substitutes the value of x by 1.3 where in f. And as you see here, as it was recommended in the question, we should put this value here in some temporary value or variable called q. So q is equal to f dot subs of x, and 1.3 means x is going to have the value 1.3 where in f, and q is going to get this value. So here q gets the value of f at x equals 1.3. And I will also print out q. So I'll write a message saying that print q equals q. So this is what's going to be displayed. Q equals minus 1.1. And that's f of x at 1.3, of course. Okay, I have the same thing that appeared here in my Jupyter notebook file. That's the q equals 1.1, minus 1.1. In the third question, I was asked to do what? I was asked to plot f of x. So for this, question 3, let us now plot the graph of f of x. We use from SMP, from SymPy, we use the function plot f. So automatically you're going to have this. That's going to be displayed. So that's the graph of f of x here. And remember, f of x was equal to 3x minus 5. So we should expect some linear graph. That's f of x equals 3x minus 5, of course. So now we did already 3 questions, and from my Jupyter notebook, here browser, that's the graph I got when I executed the command. That's the graph of f. And finally, in the last question, what I'm going to do, I'm asked to find the x-intercepts. To find the x-intercepts, I need to solve an equation. Here, we need to solve for f equals 0. Why? The x-intercept happens when f of x equal to 0. So to answer question 4, I will say that capital L here takes what is returned by this command, which is smp.solve_f. In fact, here what I will get, I'll get all the solutions of f of x equal to 0 in L. What is L here? Intentionally, I'm calling it L for list, because f of x equal to 0 might have different solutions, and automatically they're going to be stored into a list. Okay, not a single value. And here, to show you that what's going on, I'm going to just display the value of L at its first position. So at its first entry, which is L here, double bracket 0. So that gives the first and unique element of L, because here, in fact, I have only one solution for f of x equal to 0. As you know, 3x minus 5 equal to 0 has a unique solution, which is 5/3. Okay, and this what's going to happen here when I display f of I display L at 0 at the first position. Okay, if I have many items in my list, I need to be very precise and to indicate which position I'm asking for. Okay, and I will add some conditions to display only those I need. For example, only the solutions that are positive, or only those which are negative. So that's the solution for f of x equals to 0. I'm adding a message is x equals 5/3, of course. So we are pretty much done for the exercise 1, the last exercise from week 1. So now we start the content or the material we need to cover for week 2. And the material we need to cover for week 2 is from sections 5.2 and 5.3. The first example I'm covering in this presentation is the example where I need to estimate the area under the graph of f of x equals 1/x squared plus 1 from x equals 0 to x equals 4 using n equals 3 approximating rectangles with left hand, right hand, and midpoints. To do that, first of all, we need to define again x as a symbol, and to define f now using what we call lambdify. What is lambdify? It's kind of like a subs function, but here it's much more practical, because all what it would say is that the value of x, which is the variable, is going to be inserted into the expression of my function, which is 1/x squared, 1/1 plus x squared. Okay? And what is going to happen? Every time I ask for the value of f, I'm going to have it automatically without having to use subs. Okay, so I'm going to also define a, b, and n, so that I can just change them if the setting for my problems change. I'm going to display f of x, a, b, and n. So when I switch back to my browser, so this is what's going to appear here. That's the question, example 1. And these are the comments I have for the first part of the problem. Okay, I didn't solve anything. I'm just setting up my problem. And this is what appears when I use lambdify. I have x squared plus 1 to the power minus 1, which is 1/x squared, 1/x squared plus 1. Okay. Now, I need to move to the setting up what is going to happen if I need to use the Riemann sum, or I need to use 3 estimating rectangles or 4 estimating rectangles using left endpoints, right endpoints, or middle endpoint or midpoints. Okay, so we first have to define what we call the line space for x and the line space for the values of f at each x. So the line space for y. So we then evaluate the width of each one of the subintervals, which are the delta x's, and we will find the array, for example, of the midpoints and the Riemann sums. And here, note that, first of all, when I write this command, x values equals np from numpy, line space from A to B n plus 1 point, what happens? The line space command here generates n plus 1 points from A to B. So the first point is by default A, and it's going to create n subintervals. The last point is going to be B, and I'm going to have from A to B n plus 1 point, because you can't the end and the beginning. I'm going to have n plus 1 point. If you have x values, what's going to happen? You're going to have n plus 1 elements, and the y values are going to be the images of these fx values. So the y values array here, or list, is going to have also n plus 1 entries. Then I need to define what we call delta x, which is just b minus 1, b minus a over n, which is equal to the width of each one of the subintervals. And if I need the midpoints, each one of the midpoints is going to be the x values entry plus the x values entries at the previous position divided by 2. Okay, so this way I'm going to have an array also for the n midpoints of my n subintervals. So I can also display the midpoint. So what's going on in my Jupyter notebook here? I did the same thing I have in the presentation. And what I first of all, I added something. I wanted to make sure that everyone understands what are the x values. So what I'm first displaying here, when I say display x values, is what you see there. So these are the x values. And since n is equal to 3, I'm making sure that I have n plus 1. So 4 entries here. You see the first one is A, which is 0. The last one is B, which is 4. In between, I have these are the limits of each one of these subintervals. I also find the y values, and then I also displayed also the midpoints. These are the midpoints of my subintervals. Okay. So now that I have the midpoints and I have the left endpoints, the right endpoints, I'm gonna just compute the Riemann sum. If I need the left points, I'm gonna do it. If I need the right endpoints, I'm gonna do it. The midpoints also. So what are the left endpoints? The left endpoints are all the points on the y values. That's the height of each one of the subintervals of the rectangles. The height of each one of the rectangles is going to be given by the y values when you start from 0, but you end at the position which is before the last, so minus 1. So you go through the whole list of the y values, but they stop at the one before the last. These are the left endpoints. And you multiply each one of the heights by the common width, which is delta x. So now that you compute the sum, what happens? You have the sum of the areas of all these rectangles using the left endpoint method. If you want the right endpoint methods, you will start from the first position in the list in y values until the end. So you don't start from 0, you start from 1.33. Okay, with the left endpoints, you started from 0, or the value of f at 0. With the right end value, you start from the value of f at 1.33. You sum up all the areas when you multiply the heights by the delta x. So this variable, which is RER, is going to be the Riemann sum using the right endpoints. Well, Finally, if you want the middle point or the midpoints, you're going to just use the y values, the height, which is given by the value of the function using the y values, times delta x. So finally, you can print out all what is required. So the approximating the area here using the left endpoint gives you 1.97. Using the right endpoint is 0.72. And using the midpoints is 1.29. Okay. Now the question also, in the next question, we're going to be asked to plot the graph for this function. So now let us try to plot the graph of f evaluated at the endpoints. To do that, we need to define what we call a figure with some size. Here it's 8 by 8, so it's kind of square. And we're going to use the plot command or plot function, which is going to be plotting the x values with their corresponding y values. So this is what happened exactly in my Jupyter notebook when I did the same. I plot the x values with the y values using the same size, 8 by 8. Okay, this is my plot. Now I can also do more. I can even plot using the line space. And here in purpose, what I did, I've taken 100 evaluations between A and B, between, let's say, 0 and 4. So for more values here, they compute more values. So I have a more smooth representation of my function. And this is what you will see in slide 10 of your presentation. Here, we may use more points to have a smoother graph. So here, what did I say? As we see in this figure, the curve of the function is not smooth enough, as we know. So we need to expand the line space for more values. I've taken like 100 points, and I have generated all these x more values list, their corresponding y more values. And I'm plotting the graph using the x more values and the y more values. And this is the graph, which is much more smooth. Okay. Now, what else I can do in slide 11, I can do more by graphing these rectangles using the Riemann sum by the 3 subrectangles using the left endpoints or the right endpoints. To do that, what I consider is that here I'm using the x left values, which are those extracted from x values, just starting from 0 till the one before the list, till -1, from 0 till -1. So I'm using x left and y left using in my bar representation. That's the purpose of the bar representation, to plot these subrectangles. Okay, and that's the graph I have in my browser, in my Jupyter notebook browser. Okay, this bar representation kind of the plot function, but using bars instead of the plot. And I can make this bar presentation also above the same representation of I've used for the x values and y values. And here I can see that the bar representation is above the plot representation. Okay, and there are some options also for the contour or the width of the edges. You can see here, for example, for the color, edge color is B, and you align the edges or the thickness of the lines also. Okay, I can do the same also using the right and point rectangles. Okay, first of all, I'm plotting the graph, and then I'm adding the rectangle using the right endpoints. Okay, I can also finally do the same using the midpoints. And this is what I'll get here in slide 12. Okay, so basically, to summarize here what we've seen different ways to use to return or to extract back from a function the value of f using either the substitution and the question we've seen from week 1, or using the lambdify. We've seen also how to plot the graphs using plot or bar. And we've seen also how to compute the Riemann sum estimation of an area using right endpoints, left endpoints, and midpoints. So what is left from this representation is just a case here where we've taken 40 evaluation or 40 rectangles, and you see these different representations for our graphs with bars. Now, for next week, this is what I recommend for next week, is to consider this problem where we have f of x equal to square root of 1 plus 2x. And we would like to write a program that calculates that approximates the area of the region under this curve. And we'd like to make it interactive with the user. So we'd like the user to enter the interval endpoints, A and B, and the desired number of rectangles using left endpoints. So there is a hint. You may need to use the following commands, which are input, float, and int. Input would take the input here from the user. Okay, so thank you very much for today, and hopefully you are enjoying the ride. And if you have any question, don't be shy to ask. Thank you and goodbye.